Okay, we'll now take a look at a confidence interval for a population proportion. So, in the sample size, if the sample size is 240 and there are 24 successes, construct a 90% confidence interval. Give your answer to 3 decimals. So, we have here the sampling distribution of sample proportions, and at the center of the sampling distribution of sample proportions, we will have the population proportion. All right? So, in this sampling distribution, the given p hat has its place. So, the specific value of p hat that we're given here is that p hat is equal to, well, the number of successes is 24, and the total number of trials is 240. So therefore my value, the point estimate, p hat, is 0.1. So I have a point estimate of 0.1. Now, that falls somewhere in the sampling distribution of sample proportions because it is a sample proportion. So wherever it lands in that sampling distribution, it's either to the left or right of the actual true proportion, but it is somewhere in the sampling proportion or in the sampling distribution of proportions. And what we're going to try to do is we're actually going to try to create a confidence interval for this point estimate, because our confidence in the population proportion being exactly 10% is 0. We don't have any confidence. But if I increase and made an actual interval of estimates, I could have a little bit more confidence instead of a one single number. Because, I mean, the chances of it being exactly equal to 10% are 0, so we're going to create an interval. To create this interval, we're going to look at the spread of the sampling distribution. And in order to do that, what we're going to try to do is we're going to try to capture 90% of all of the sampling distribution proportions by our interval. So we're going to start at p hat, the point estimate. We're going to extend above it and below it to try to capture 90% of the sampling proportions. So in the sampling distribution, I first have this initial estimate, this point estimate. I'm going to extend above and below it to create an interval, and I want that interval to capture 90% of all of the sample proportions. So I need to know something about the spread of the sampling distribution, and thank goodness the standard deviation of the sampling distribution is actually what we call the standard error. And we don't actually know what the standard error is unless we know the population proportion. So what we're going to do is we're going to use the sample proportion, p hat. We're going to use that to estimate the standard error. So to estimate the standard error of the p hats, it's actually p times 1 minus p over n. But because we don't know the population proportion is what we're trying to estimate, we're going to also estimate the standard error by using p hat, the point estimate. If we do that estimation, we get, well, the square root of 0.1 times 0.9 over 240 is going to be 0.0194. So the standard error, the spread of this thing, is 0.0194. And because the success failure condition is met, because 10% of 240 is 24, and we have at least 5 or at least 10 successes, because we have at least 10 successes and at least 10 failures, we know that the sampling distribution is a normal distribution, and that normal distribution, that sampling distribution is a normal distribution that has a mean of p, like we said earlier, but the variance of this thing is actually the square of this standard error, p hat, or approximately equal to p hat times 1 minus p hat, because remember, this is only an approximation, over n. So basically, we know what the spread is because we know the variance, and we know for normally distributed population, most of the values lie within 3 standard deviations of the mean. And if you go out to 2 standard deviation, that's roughly 95%. We're looking for a 90% confidence interval, so we want to extend far enough up and down that we capture 90% of all the sample variances. So what we're going to do is we're going to look at the z-score because we know it's normally distributed. because it meets the success failure, it's nearly normal, we're going to use the z-score that separates the 90% in the middle from the 5% below and the 5% above. If we were trying to create a 95% confidence interval, we'd use this z-star. 99%, we would use this z-star. But because we're trying to do 90, we're trying to use the z-star that separates the 90% in the middle from the 10% below and above. So that's 1.645. And that means that when we're calculating the margin of error, what we're going to do is we're going to go 1.645 standard errors above and below the mean. So the margin of error is this many times the standard error. So 1.645 is the number of times I have to go above and below the sample proportion with the standard error here. All right, so what does that mean? That means this distance from this dot to this vertical bar, that distance is 1.645 times the standard error, which is 0.0319. It's also the same distance from here to here. That distance is also the same from here to here. So I'm going to surround p hat with this margin of error, left to right. So the actual proportion, if I did this process of creating this confidence interval over and over and over again, I would expect this process to capture the true population proportion 90% of the time. So I am 90% confident that the proportion P, the population proportion, is between P hat minus the margin of error, which is this down here, and P hat plus the margin of error, which is this point up here that separates that 90% in the middle. So there's my P hat, 0.1. There's my margin of error. I'm subtracting it. There's my P hat, 0.1. And there's my margin of error. I'm adding it. So I think that P is somewhere between 0.68 and 0.132. So I'm 90% confident that if I do this over and over, my proportions will capture or I should say, if I repeat this process over and over, 90% of those intervals I create, I would expect to capture the actual true population proportion. This is one of those intervals. That's my 90% confidence.